Alright, so today I'm going to be explaining another important article with the title Higher Order Clustering and Pooling for Graph Neural Networks. This important paper in 2022. Graph neural networks achieve state-of-the-art performance on a plethora of graph classification tasks, especially due to pooling operators, which aggregate learned node embeddings hierarchically into a final graph representation. However, they are not only questioned by recent work showing on-par performance with random pooling, but also ignore completely high-order connectivity patterns. To tackle this issue, we propose host-pool, a clustering-based graph pooling operator that captures higher-order information hierarchically, leading to richer graph representations. In fact, we learn a probabilistic cluster assignment matrix end-to-end, minimizing relaxed formulations of motive spectral clustering in our objective function, and we then extend it to a pooling operator. We evaluate host-pool on graph classification tasks and its clustering component on graphs with ground truth community structure, achieving best performance. Lastly, we provide a deep empirical analysis of pooling operator under functioning. So higher order connectivity patterns like motifs, small subgraphs like a triangle, they are known to be fundamental building blocks of complex networks. They are essential for modeling and understanding the organization of various types of networks. For instance, they play an essential role in the characterization of social, biological, or molecular networks. So this reference showed that that vertices participating in the same higher order structure often share the same label, spreading its adoption to node classification. We have talked about normalized cut problems several times in the previous videos. So the same idea can be used for motive conductance. Instead of the traditional conductance, we can have motive conductance. So M is the set of all instances in G, the set of all motives in G. So it's a higher order looking at the graph. So the method is like this. We focus on triangle motifs, so consider K3, and extend to more complex motifs. So we calculate the cut, the volume in order to calculate that objective. So the last equivalence follows this form. Instead of using partitioning sets, we define a discrete cluster assignment matrix S. That, for example, you know that if it's an indicator, which indicates the nodes belonging to cluster Sj. So we can transform this into something that we are familiar with. Trace of S transpose AS divided by S transpose DS. So everything is the same, just it's on a higher order level, at the level of motives. So we leverage this probabilistic approximation of motive conductance to learn our cluster assignment matrix in a trainable manner. Our method addresses the limitations of motive spectral clustering. We cluster nodes based both on graph topology and node features, leverage higher order connectivity patterns, avoid the expensive eigen decomposition of motif Laplacian, and allow to cluster out of sample graphs. We compute the soft cluster assignment using one or more fully connected layers, mapping each node's representation to its probabilistic cluster assignment vector. So we apply a softmax activation function to enforce the constraint inherited from 4. We allow combination of several motifs. Our objective function denotes the objective with respect to particular motifs. So the graph coarsening step will pull together more relevant groups of nodes, potentially capturing more relevant patterns in subsequent layers, ultimately producing richer graph representation. So we implement it for edge and triangle motifs. So alpha 1 and alpha 2 are dynamic functions of the epoch, subject to that the sum is 1, allowing to first optimize higher order motifs before moving to smaller ones. It helps refine the level of granularity progressively and was found desirably empirically. This is the higher order clustering formulation that we consider in the paper. So the methodology detailed in the previous sections is a general clustering techniques that can be used for any clustering task on any graph dataset. So we utilize it to form a pooling operator, which exploits the cluster assignment matrix to generate coarsened version of the graph with fewer nodes and edges that preserve critical information and embeds higher order connectivity patterns. More precisely, it coarsens the existing graph by creating supernodes from the derived clusters with a new edge set and feature vector depending on previous nodes belonging to this cluster. Finally, we add all of these by jointly optimizing end-to-end. So we compare it with state-of-the-art, and the baselines like min-cut pool, diff pool, these are very important. And you will see that for example, PubMed dataset, the diff pool is 80, the running time is 80. Min-cut takes a longer time, but these methods, because they are higher order structures, so this is the drawback of this approach. The time complexity is too high. But of course, there is a trade-off between time complexity and accuracy. But it is more accurate. It takes time, but it is more accurate. And you will see that, for example, for proteins data set, 77% in comparison to diff pool or min-cut pool, which is, for example, 2 or 3% improvement. So you see, you get accuracy, but it takes time. So trade-off between time accuracy. And they use it for different kinds of data sets like karate, PC, photo, PubMed, Quora. Of course, instead of just triangle, they can extend it to 4 nodes motifs. But the problem is, the kind of structure is arbitrary. It could be anything. So that one adds one more time to the complexity. to the computational complexity of the problem.